All right, physicists, let's take a look at these uniform circular motion questions. These are the ones on the green sheet. The first one is the looping coaster. So it says the minimum speed needed to safely complete the loop of a particular looping coaster and not fall out at the top is 8.9 meters per second. And then it says, based on this, determine the radius of the loop, and then we'll do part B in a little bit. So let's go ahead and draw a picture because that's a really good place to start if you're not sure what to do. So we're going to draw ourselves a loop and we'll put a roller coaster car at the top of the loop and then draw a free body diagram. So what forces are acting? Well, I think probably we've got the force of the earth. I'm just going to write these quickly. So we'll just say the force of gravity and anything else acting. There's no string attached or anything like that, but thankfully the roller coaster itself, like the track is there, and that is pushing down on us as well. So we're going to go ahead and put that force in there as well, F. And it's a normal force because it's just the surface of the track pushing down on the car. So if we write down an F net equation for that, then we've got F net in the y direction is equal to, well, we've got Fn plus Fg. They're both pushing in the negative direction and causing a negative centripetal acceleration on the car. So it says here that it's the minimum speed. So we need to think about what that means. I'm going to go ahead and write down that this is really mv squared over r. I'm just going to take that negative sign out since there's a negative each one of those. So if we think about this, the minimum speed is going to be the smallest value of v. And if we're talking about the smallest value of E, that's going to be the smallest net force as well. Now, we know, of course, that Fg is just mg, and that's not going to change regardless of how fast or slow this thing goes. But the normal force can change, right? The normal force is just the force of the surface pushing, and that can change. So the smallest value of the net force is going to be when this sum is the smallest, and the smallest that the normal force could be would be 0. So we're going to go ahead and set that equal to 0. So this would be just when it's just barely going over the top before it finishes its loop. Luckily for us, when roller coaster designers are at work, they make sure that the car is going much faster than the minimum speed. But now we can just kind of take a look at what the physics is here. So mg is going to be equal to mv squared over r. And again, kind of like we said with the car going around the curve, thank goodness that the masses are going to cancel. And so now we can easily use this to figure out what the radius is. So we're just going to solve for radius. So we've got r is equal to v squared over g. We know that the velocity is 8.9 meters per second, and g is 9.8 meters per second squared. We're going to square that v, by the way, and I think that gives us a radius of about 8.08 meters. Okay, so that's part A. And then for part B, let's take a look at what this one says. So part B says the roller coaster actually moves faster than the minimum speed. Let's say that it moves 12.2 meters per second through that loop. It asks to determine the centripetal acceleration based on the car's actual speed. So centripetal acceleration is just a sub c. So that's, we don't need the m there. I almost tried to write it, but it's not. It's just v squared over r. We know the radius. We found it in the first part of the problem. We know the velocity because it gave it to us there, 12.2 meters per second. And then going ahead to plug in our values, we've got 18.4 meters per second squared. So that's a little bit more than our regular acceleration due to gravity, but it's not so much that our bodies are going to not be able to handle it. All right, there you go.